Hello. In this video, I'm going to talk about data tables, variable standardization and correlation matrices. The idea is to introduce some concepts that help you understand your data better. I'm going to be using some concepts from the previous videos, in particular matrix multiplication, inner product and outer product. So if you don't know those concepts, please review the previous videos. Okay, so what is a data table? A data table consists of data, items, or samples or features in rows. So what do we have here? We have different kinds of cola. So each cola I can think of as a sample. And these are characteristics of the cola. So I could think of these columns as representing variables. And these variables, as I said, characterize the different colas. So all of these variable values belong to Coca-Cola. All these belong to Diet Coke, etc. Right. So the data table rows I denote as sample vector, data vector, or feature vector. I may use those terms equivalently. Each column is a variable vector. All right. Now, let's look at these variable vectors and some possibilities. Sometimes variables are closely related. For example, if I take degrees in Celsius and degrees in Fahrenheit. So here's a table that lists the degrees in Celsius and in Fahrenheit. And these are two variables. And in fact, if you drew a graph, you would see that they are very closely related. In fact, they're linearly related. In fact, there's a formula that relates the first graph to the second graph, right? You have you have f equals 9/5. Let me just write it down here. If I can get there, f equals 9/5 c plus 32. So if I know what c is, I can find what f is. Really, these two variables do not give me different information. The information is redundant. So it's important for me to be able to identify such cases. So what can we do in this case? One solution is to standardize the variables. One common standardization is the z-score standardization. And here are the steps for doing that. Subtract the mean from each component of the variable vector. So y equals x minus mu times 1, where x is a variable vector, mu is the mean, and 1 is the vector of all ones. Well, let's do that, for example, up at this example. If I was going to standardize the first column, first I would have to find the mean of this column. So I'm going to go offline for a second and compute the mean. So I copied my numbers into a spreadsheet here. And I'm going to take the mean of each column. I think it's average in Excel. And there we go. And I'm going to take the average of these. Okay. All right, so it's 10.35. Let me leave some space here. I'll do the same thing for this other. And let's insert another column here. All right, I'll do the same thing for this column here. I'll take the average of the column. Whoops, sorry, didn't take it. All right, average, there we go. And then we take the column. All right, so we get a number there. Make sure I grabbed anything. Okay, so the second step, according to this, is I need to subtract the mean from each element of the vector. Okay, so I'll go here, and here I'll just copy the mean, this value, and I have to do fixed reference, so I'll have to do like that. Okay. I'll just take this vector here, and I'll subtract that. Here, I'm going to need another space here. Let me leave a little more space here. So I'll do it all together for this vector first, and then you'll see how it works on this vector here. Okay. So I have to subtract the mean. Okay. So I take this minus this, and I'll fill down, and I'll get all my values. Right? Then I want to take the sum of squares of these values. So I'm going to take equals sum. I think I have a sum of squares here. Sum of squares here. That's an Excel function. And I'll do this. And I actually want the square root of that, so I'm going to add a square root in front. Okay, sum of squares. Okay, I'm taking the square root of the sum of squares, and I get 42. And then what I'm going to do is I'm going to divide this result. Well, I can just divide this result and divide it by this sum of squares here. So I'll do that F4 like that. And then here's my values. Okay. So there's my values for the sum of squares. All right, so let me see if I can do the same thing on this here. All right, rather than making a column like this, I can just directly subtract the mean. So I'm going to take, so this is going to be equal to this minus the mean value is here. Okay. I have this, and I'll pull down. And then I want to take the sum of squares, square root of the sum of squares, so it's equal to square root of the sum of squares. Sum square. Okay. And that's going to be these values here. Okay. And close it. And then we will go ahead and divide this value by this square root of sum of squares. And lo and behold, we get, whoops, sorry, I made a mistake. Go back here because I didn't make the fixed reference in the bottom. So I'll make a fixed reference in the bottom. And I'll go here, and lo and behold, see if it works this time, you get exactly the same numbers. Okay? So what you've done is you stripped off the linear difference between the two series. Right? So standardization is a very important way of putting your variables in a form so that if there's a linear relationship between the variables, it will become very clear. Right? So here we have z-score standardization. Okay. And I guess I did the exercise for you, but you can actually work out the mathematics that if you have two variables that are linearly related, they will give you identical standardized vectors. All right, now look at this quantity here, sigma squared. This kind of looks familiar from basic math. Sum of squares, you may know something about variance, but even farther back, you have geometry and you have hypotenuse. Hypotenuse is a sum of squares. So where am I going here? I want to give some geometrical intuition behind these data manipulations, because in order to develop intuition, you need to have some pictures to relate what you're doing to the data. All right? So the geometrical length of a two-dimensional vector, everyone's familiar with this. Now the same thing happens in 3 dimensions. Here's a 3-dimensional picture. You can see the flat plane down here, and then the 4th dimension. And this is a simple derivation that the length of this 3-dimensional vector is in fact the square root of the sum of the 3 squares. Right? The way you do that is you get this c as the square root of the sum of 2 squares, and then you use Pythagorean theorem again to get the 3-dimensional vector as a square root of a sum of 3 squares. Now it turns out that you can do this in any number of dimensions. Now you might say, wait a minute, there aren't more than 3 dimensions. Well, we're talking mathematically here. If we have a list of n numbers, I can treat that as an n-dimensional vector. So don't think that geometrical vectors are the only kinds of vectors. We can have vectors that consist of other quantities. In fact, in modern physics, they use space and time, so that's 4 dimensions. And you can use dimensions. You can see here that I have 3 dimensions for each one of these items. The number of variables I have, I can consider as different dimensions. Okay, so this idea of geometrical length is also useful in higher dimensions when you're doing higher, we're dealing with higher dimensional data, and you're dealing with vectors that have several variables. Okay. Now, another exercise is show that the geometrical length of a standardized variable vector is always equal to 1. Okay, it's actually a simple, fairly simple exercise. I'll show you how that works on our spreadsheet here. All right, here is my standardized vector here. So let me leave myself a little bit of space. Okay. And if I want to find the sum of squares of this vector, let's go ahead and do that. I have my handy dandy Excel function to do that, sum SQ. And I'll take this and we will see if I'm right. In fact, we get 1. So it works out kind of because you're making it work out by your division. Right. So what does this mean? So I can have a geometrical representation of my data. If I have a data table with n data vectors and m variables, and I standardize the variables column by column, this will give me m standardized variable vectors of length n. Right? I'm standardizing column by column. Each column is going to give me a vector. In this case, I'd have 1, 2, 3, 4, 5, 6, 7 dimensional vectors. I have 3 7-dimensional vectors. And they all have length 1 after I standardize them. Right? Now, of course, I can't plot 7 dimensions, but I can give a 2-dimensional analog that will give me conceptual aid to understand what I can do in 7 dimensions. One of the wonderful things is the same principles work in 2 dimensions, 3 dimensions, and higher dimensions. And you can use your geometrical intuition in the lower dimensions to get you ideas about the higher dimensions. So here I have 2 unit vectors in 2 dimensions. And of course, they both lie on the unit circle. Right? You can imagine, I'm not very good at drawing, but you can imagine in 3 dimensions, you'd have 2 points on a sphere. Now, the question is, how different are these 2 vectors? And one way to measure the difference would be to measure the arc length between them. These 2 vectors seem fairly similar because they're nearly in the same direction. Now, if I had done this with the Fahrenheit and centigrade, they would be in exactly the same direction, but here they're nearly in the same direction. So I can measure the difference between them by taking the arc length here. Now, it turns out that that's not how it's done with data. So here, let me read this through. So my question, how can we quantify the degree of relationship between standardized variables? In response, since all standardized variable vectors are points on the sphere of radius 1. Now, I said sphere or circle. I should say on an n sphere because it's n-dimensional. Then one way of measuring the difference between them is the arc distance or angle. Now, if this is a unit circle, then this arc distance is in fact equal to the angle. All right? The smaller the angle, the closer the relationship between the 2 vectors. They'll really resemble each other very closely. But by convention, and for several reasons, we use the cosine of the angle rather than the angle itself to indicate the closeness of 2 vectors. Now, if you're kind of rusty on your trigonometry, and you thought that you'd never use it, trigonometry comes all over the place in data. So, so we're looking at the cosine. Now, I can stop and give you a graph of the cosine, just to give you a 1-minute background. So when I did a Google search for cosine and look for images, this is what comes up. You can see that the point on a unit circle, the x-coordinate is the cosine, the y-coordinate is the sine, and cosine is a function of the angle. If I was going to graph cosine as a function of angle, it would be this wavy curve here. But what's important for us at this point is more this picture, where the cosine of an angle is equal to the x-coordinate. Right? So let's go back to our problem. Oh, so let me pull that out one more time and show you. Now, as the angle gets smaller, the cosine gets closer and closer to 1. You can see that. Right? Because if I'm right here at angle of 0, then the cosine is 1 because the x-coordinate is exactly the same as the location of the point on the circle. On the other hand, as theta increases, as the angle increases to 90 degrees, the cosine becomes 0. And you can see that same relationship over here. Cosine is 1 when the angle is 0. Cosine goes down to 0 when the angle is, well, 90 degrees or pi over 2. All right? So that's a lightning review of cosine. Right? So by convention, we use the cosine of the angle rather than the angle itself to indicate the closeness of 2 vectors. The larger the cosine, the closer the relationship. If the two vectors are identical, the cosine is 1. Okay, so that's what I said. Okay, the cosine of the angle between two variable vectors, v and w, is called the correlation, or correlation coefficient. That's what a correlation coefficient is. It's the angle between two vectors of unit length. And those two unit vectors are the standardized vectors that correspond to your variables. So you may think about that. I think probably many of you have used correlation before, but the geometrical intuition behind it is as an angle. There's a cosine of an angle. Okay. All right, so often the correlation is denoted by the symbol rho. Okay, for instance, if you have two vectors v and w, sometimes they'll write rho vw. I believe the textbook uses this. Sometimes you may see this. Sometimes you may just see CORR for the correlation. Now, this is not a P, it's a rho. All right. Now, why do we use cosine? It turns out there's a general formula for rho of VW that's both simple and extremely powerful. And this also comes back from trigonometry. All right, let's look at what happens in 2 dimensions. Okay, so here I have my two data vectors. And as I mentioned, the cosine is the x-coordinate of the vector. The sine is the y-coordinate. Okay, so here's my x-axis, my y-axis. Cosine is the x-coordinate, sine is the y-coordinate. And that's because the point lies on the unit circle. So here I have two data vectors. And the angle between them is the difference between the angle for the first one and the angle for the second one. So here I wrote cos A sine A, but in fact, if I think of this in terms of my data vector, cosine A, that's the same thing. Let me call this data vector x. I would call this x1, x2. Let me call this vector, what did I call it up here? What did I call it up here? Oh, I said z and w, so let's call it z. Okay. Doesn't really matter, it's just a number, it's just a label. So I'll call this vector z1, z2. Okay. That's the z1 is the x-coordinate, the z2 is the y-coordinate. And I'll call this w1, w2. Okay. And I want the cosine of the angle between these two, the cosine in this case of a minus b. Now if you go back to your angle subtraction formulas, and go back to your trigonometry textbook or look online, the cosine of a minus b is equal to cosine A cosine b plus sine A sine b. Now what's cosine A cosine b? Well, that's just the product of the x-coordinates of the two vectors. Right, so here I said v, so I should make this z in this case. Right, so this is z1, okay. Right. So I have this product. Now, I hasten to add that this formula applies only if the vectors are unit vectors. And sorry, I'll change that to a z again. Okay. All right. Now, this is in 2 dimensions. It turns out that the same formula works for in any dimension. Oh, sorry, I need to make a v. So give me a moment to fix this, and I'll be back online in a second. Okay. I got this fixed up now. This is vector v1, v2, and I have my distance, my cosine, v1, w1 plus v2, w2. And the general formula is just the sum of the products of corresponding components. All right? All right. Now let's go back to our data. We have our data table, and we've normalized the columns. So the columns are n-dimensional unit vectors. We can form m-squared correlations from these m vectors. That's because I can take any column and correlate with any other column. Right? So I have m choices for the first column, m choices for the second column. That gives me m squared choices altogether. Okay? These m-squared correlations can be arranged in a matrix. Okay? You knew we'd get back to matrices. And this matrix is called, appropriately enough, the correlation matrix, which we will denote as C. And in the literature, people call this by different letters, but I'm going to call it C. So the entry in row I and column J is the correlation between vector I and vector J. Okay? So I can denote the matrix this way. See, the entry in the first row, first column would be row v1, v1. The entry in the first row, last column would be row v1, vm. So here I have v1, v1, second entry v1, v2, v1, v3, etc. Okay. If I go down the rows, then this one below would be row v2, v1, row v3, v1, all the way down to row vm, v1. And if I go across here, row vm, v1, vm, v2, etc., down to row vm, vm. Okay. And what I'm doing is taking correlations between vectors. If I go back up to this example here, if I was going to take correlations, this would be v1, v2, v3. So v1, v1 would be the correlation of this column with itself. v2, v3, for example, would be the correlation of this vector with this vector. Now, one thing you may notice is that if I take the correlation of v2 with v3, that's the very same thing as taking the correlation of v3 with v2. I can exchange the v1 and the w1 and the v2 and the w2, and I get the same answer. So it doesn't really matter what order you write the vectors in. Okay? So row vi, vj will be row vj, vi. So the correlation matrix is symmetric. And symmetric means that I could take this matrix here and I could flip it across the diagonal and it would be the same. This entry here is the same as this entry here. Okay? All right, now, it turns out that the correlation matrix is in fact the matrix product of two matrices. All right, so that's the whole build-up from last video, why we're doing matrix products. Now, this should not be too surprising because if you look at this, this is actually an inner product. It's an inner product of this row vector v and this column vector w, or vice versa. Right? So let's see how the matrix product works out in this case. If you look here, each one of these correlations involves n terms. Now, if you remember when we multiplied matrices, the number of terms was equal to the number of intermediate steps. The matrix also has m rows and m columns. Remember that m is the number of variables. So we have our input states and output states both are m. So what this is telling us is that our input states and output states all correspond to the variables, and the intermediate states correspond to the data rows. Right? By the way, notice this row v1, row v1, v1. This value is going to be 1. You can think about why that is. All the diagonal entries here are going to be 1. And the matrix is symmetric, as I said before. Let's scroll down and see how we're going to make this work. Okay. The final inputs and final outputs are both the variables. The intermediate states are the samples of rows of rows of the data table. All right. So this picture is showing a case where there are 3 rows and 2 variables. So let's go back up here. That means we're only dealing with a data table, something like this. 3 rows and 2 variables. So we're just dealing with this portion of the data table. All right. So you can see that the first data row involves 2 variables. Second data row involves the same 2 variables. Third data row involves the same 2 variables. So we have lines from the 2 variables to each one of the data rows. So that's what's showing down here. Variable 1 and variable 2 all connect to the 3 rows of the data. But these 3 rows also connect back to the variables. And in fact, these 2 lines are labeled with the very same value. Right? This here is going to be the value of variable 1 in row 1, the same as here. This value here is going to be the value of variable 2 in row 1, and so on. So when we work out the matrix product, for instance, if I was going to take the correlation between v1 and v2, well, this is old hat for us. We just take this line, this line, and this line. Okay, so it's going to be this entry times this entry, plus this entry times this entry, plus this entry times this. Let's be a little bit more specific. We need some way of notating the entries of this data matrix. And what's typically done is the entries of the matrix are specified by a letter and then two indices. The first index is the row index, and the second index is the column index. And that's actually what I indicate down here. Right, so the ij entry of data matrix is denoted by zi, comma j, or zij. Right, so they sometimes use different letters except besides z, but the use of subscripts is common. Right. So in this case, this is first row, first column, so it's z11, first row, second column, z12, this is z21, z22, and then z31, z32. Okay. So the numbers in this matrix on the right here express the relationships that are shown on the left. Right? This matrix on the right represents the relationships here. Remember, the inputs are the columns, the outputs are the rows. Right? So the lines corresponding to V1 here correspond to the entries in this column here. So here I have Z11, Z21, and Z31 for those three. And then for the other three, I'll do in a different color to try to make it a little bit more clear. This one is going to relate to this column here. So this is Z12, Z22, and Z32. Okay. On the other hand, the matrix here is going to relate to the relationships on the right. Now, we're just running the relationships backwards here. So this matrix is the same matrix here, just turned on its side. So the first row here becomes the first column here, Z11, Z12. Second row becomes second column, Z21, Z22. Then Z31, Z32. So we can similarly relate the entries in this matrix to the connections here, right? This is Z11 is the one that relates X1 to V1, so this is Z11. And you can also note the symmetry here. This Z11 here that connects the V1 here to the X1 here is going to be the same value as that connects from X1 to V1 back again. So the same way that we've labeled this Z11, Z21, Z31, that's going to be Z11. Then Z21 will be the entry that relates V1 to X2. So this is Z21. And then this is Z31. Okay. And then the entries that correct to V2, that's going to be the second row here. This is Z12, and then Z22, and then Z32. Okay. All right, so that's how it works out. And you can work this out and see that everything is consistent. The matrix multiplication here does in fact correspond to this diagram. All right. A little bit messy, but hopefully you could follow along with my discussion. All right. So here we have the data matrix, original data matrix with our z's. Remember that these z's have been rescaled, standardized, and then I take the transpose. If I take the product of these two, I get the correlation matrix. Now, from an outer product point of view, the correlation matrix is the sum of the outer product of each row of the data matrix with itself. Remember, we said that we could view the matrix product of two matrices in two ways. One is view each entry of the matrix as an inner product. The other is to view the product itself as a sum of outer products. All right, so I've written the two matrices again, the transpose and the original data matrix. And there's going to be one outer product corresponding to each intermediate state, x1, x2, x3. First outer product takes the data row, the first data row, and outer products with itself. Second outer product takes the second data row, outer products with itself. Third data row, outer product with itself. And I can write out these outer products the same way as before. If you remember, the way this works is that the diagram looks like this. This would be V1, V2. This, for instance, in the first outer product would be X1. I'd have V1, V2 here. Now this is from the first variable to the first row. So this is going to be Z11. This is from the second variable to the first row. So this is going to be Z12. This is from the, and these are symmetric here. So this is also Z11, Z12. So if I relate my inputs to my outputs, V1, V2 here, V1, V2 here. Okay. The connection V1 to V1 is Z11, Z11. The connection from V1 to V2 is, so this is the input, this is the output, input, output. So this would be, let's be careful here. So this is the input, this is the output. So that would be here. That would be Z11, Z12. Here, this is the input, this is the output, go from V2 to V1. And it turns out that that's the same thing, Z12, Z11. And then if V2 is the input, V2 is the output, that will take me here, Z12, Z12. Okay? And I get the same matrix I got up here. All right. And similarly, I could diagram the other outer products. Okay? So in the next video, we will relate these properties to information about the shape of your data, ways to characterize the data in meaningful ways. All right, so thanks for watching.